Welcome to my presentation about our hybrid MPI correctness benchmark suite. The idea behind this work is that programming a correct MPI application can be quite complex. Yeah, and similarly goes for OpenMP. Basically, the more threads you have, the more processes you have, the more complicated things can get. And then when you add those two together, you have several MPI processes, and each process has a different amount of thread maybe. Then things can be even more complicated. So therefore, it would be a good idea if we have tool support that the tools can then tell us about the errors that we've made and maybe also offer some insight on how to fix those errors. So there have been developed tools for OpenMP and for MPI that covers correctness. Yeah, in this work, we consider MUST and ITAG as tools for MPI correctness. We use these tools as there are common tools, and they do actually support MPI thread multiple as the threading level, which is great if we want to test MPI plus OpenMP applications. These two tools are dynamic tools, meaning that the way how the tools work is you execute the program under the tool's supervision. And then at the end, when your program has finished, you will get an error report, hopefully telling you that you have done no error. But sometimes, you will get a detailed error report detailing all the errors that were in your program. So the next question that you can ask then is, okay, we have those kinds of correctness tools. How good are the tools? Yeah, and therefore there have been suggested several correctness benchmarks, such as Data Race Bench for correctness of OpenMP programs, our previous work, MPI Core Bench, or the MPI Bugs Initiative for correctness of MPI programs. So the question that remains there is that how do the tools perform when we then use them on the hybrid application? And also, are there any new possible types of errors that we can make once we add several threads to our MPI application? So let's have a look about the different MPI errors. So there are a couple of error cases that we will not consider for our hybrid case, such as erroneous argument, mismatching argument. Yeah, for example, if you give an MPI send call a null pointer and then send a message with non-zero message length, this is an error. And we do not consider this as a hybrid error because if you then add multiple threads, there is no additional layer of complexity added in those kinds of errors. It's sort of a local error to this specific MPI call, and you just have to check whether or not all the parameters that go into this specific call are correct or not. In contrast, there are other errors, especially these concurrency-related issues, message races, concurrent MPI usage with non-blocking operation, where you have an additional layer of complexity added when you use multiple threads. Yeah, so for a non-blocking operation, you have to make sure that while the non-blocking operation is in progress, no one modify the message buffer. So when you have just one thread, there is of course the possibility of errors, but then if you have multiple threads, you do not only need to make sure that the thread issued the non-blocking operation, they should not change the message buffer, but all other threads should also not change the message buffer. So here you see there are a couple of more ways how you can make those errors, so to speak. And the same goes for erroneous program flow, let's say wrong ordering of collective operations, for example. So if there are no defined order between two operations because they are logically concurrent, then the question is, okay, are all possible orderings correct orderings? We also have some errors that you can make with OpenMP. Again, we have some errors that we not consider in this work, such as the violation of the single entry, single exit principle for an OpenMP parallel region, as this is like sort of a local thing that is only local to this specific thread. And there is no additional layer of complexity added when using multiple MPI processes. But again, for some other kinds of errors like these race conditions, deadlock, all these concurrency related issues, synchronizing all the threads correctly in order to prevent deadlock can become quite challenging sometimes. And then if you add multiple MPI processes to the mix that also have a couple of threads each, then preventing deadlock can become quite harder. There are also some other cases like uninitialized memory assumption on the degree of parallelism that previously were no big issues in MPI errors. But we will see on the next slide that those kinds of error categories also become relevant when using MPI in a thread multiple mode. So we have different classes of errors, some that originate from MPI, so to speak, some that originate from OpenMP, and then we combine those to get the hybrid classification. So one thing, OpenMP has this error class assumption on the degree of parallelism. And the way how it works in MPI is that you have to initialize your MPI program correctly. Yeah, so if you have an example like here, you see that there are several threads, and then you should use MPI init thread instead of MPI init with the proper level of thread support, of course. For these kind of concurrency related issues, data races, message races, so these are race conditions, we also see that such errors are present. So if we look at this code example from the perspective of a pure OpenMP correctness tool, so we have to analyze if there are any race conditions. So let us have a look here. The buffer is used, but each thread gets their own portion of the buffer, so there is no race condition there. And then only the master thread calls this function. The function uses the buffer. Yeah, but maybe the programmer does know what this is doing. Maybe they only use the first part of the buffer, the part that is actually assigned to the master thread. So in order to avoid having lots of false positives, you could imagine an OpenMP correctness tool not warning about that there is a possibility of a data race there. And similar it goes when you have a pure MPI perspective and you are looking for data races there, then you see, okay, this is a blocking MPI send call and there cannot be any data race inside of a blocking MPI call, because we assume that the MPI implementation works correct and has no data races in itself. So you see, in order to figure out that here there is a data race in this code, you need to combine the knowledge of the OpenMP semantic with the knowledge about the semantics of this MPI send call. Because there is a data race, there is no synchronization between the modification of the buffer and sending the buffer to other ranks. So it is possible for the first thread to start the sending operation while the other threads are still changing the message buffer. And then you see that you can also have these kind of data races with blocking MPI calls, a thing that in a single-threaded MPI mode was not possible. For deadlocks or erroneous program flow, wrong ordering of MPI operations, there we see here that this code example here may or may not deadlock depending on what the OpenMP implementation does. So the OpenMP implementation is allowed but not required to immediately execute this task before the other tasks are created, meaning that the thread that creates all the tasks goes into this task and then blocks until someone executes the send operation. But as the other task will only be created once the first task has finished, no one will create the send operation tasks, and then you get a deadlock. Again, the OpenMP implementation is not required to order this task. These two operations are logically concurrent, so it can also happen then when you have enough threads available that this will work just fine. So here you see this kind of transient error. Sometimes the error occur and sometimes you won't notice any issue in this code. For this particular class of errors with tasking in MPI, because synchronizing this correctly is really hard, if not impossible with the current means of synchronization. There has been suggestions such as using a task-aware MPI implementation or MPI detach as a mechanism to correctly synchronize MPI with tasking in OpenMP. Also, a common mistake that you can make in OpenMP is forgetting about that if you have an OpenMP private variable, that this variable is not initialized. And then if you then use this initialized value inside of an MPI call, this may lead to undefined behavior. So sending around the uninitialized memory to the other process by itself may not be undefined behavior, but then if the receiving rank uses the uninitialized memory in some condition, for example, then you have undefined behavior. And as this is a quite common case in OpenMP, to forget about this, it would be a great idea if also MPI correctness tools for the hybrid mode tells you about this issue. So how can we find out how good the tools are currently performing on those hybrid cases? So we have developed small scale unit tests. So one file per test case, one error per test case. And if you have a look in the GitHub repository, I post the link on the last slide, then you see that each error case also have a comment in the beginning explaining what the error is actually about. One thing that we need to take into account is this non-deterministic execution. Here we've seen an example where sometimes the ordering of execution will be correct and sometimes it won't be correct. So therefore, in order to test in which kinds of execution the tools can determine the error and which kinds of execution they miss the error, we vary the amount of threads, the load imbalance, and of course we execute each combination multiple times. In this way, we can make that the error actually occurs. We can make it more or less likely depending on the load imbalance. Of course, we don't use any synchronization in order to achieve the load imbalance, so that the operations are still logically concurrent. And then the question is, does the error occur in this given execution? Therefore, we observe if the buffer has some unexpected content due to the malicious data race, or we also observe the ordering of MPI calls that happen during execution with a logical clock. And then in the end, we can come back and have a look at the ordering and then determine if the actual order that happened during execution was correct or not. So this leads to visualization such as this. So here you have the different test cases number, and there each test case is executed multiple times. And you can have the case that for some executions, the correctness tool gets that there is an error and reports about the error. For some executions, unfortunately, the ordering of the operations were not recognized as erroneous by the tool. For some execution, it may be the case that the error was so bad that the tool and the MPI implementation has crashed. And the key thing here is for some other execution, it may be the case that the ordering of execution was actually correct in the sense that just by chance, due to the load imbalance in the thread, you get the correct ordering of execution. In this particular classes of error, when we test about wrong threading level, these correct cases are the cases that were executed with only one thread, because then it is okay to use MPI init instead of MPI init thread. So we do know that some of the errors like these here are completely missed by both of the correctness tools. These kinds of errors were when you have an MPI application that requires MPI thread serialized as the threading level, but you initialize it with MPI thread single, for example. And these kinds of errors are completely missed by both of the correctness tools so far. To be fair, if you initialize an MPI implementation with MPI thread single and then use it as if you had initialized it with MPI thread serial, most of the implementation will actually work quite well. But if you read into the standard, you see that it is an error and you should not do this. For some other cases, like this one here, where MPI finalized was not synchronized correctly and may be called before all operation has finished, then we do see that the runtime influence of ITAC, for example, made it so that the error essentially disappears. So which may be not so good if you want to use the tool. So here you see, okay, there is an error because my MPI implementation crashes all the times if we call MPI finalize before all MPI calls have finished. And then you use the correctness tool and check where is the error. You want to get more information about it, and then the correctness tool tells you there is no error, because the runtime influence of the tool in this particular case works in a way that under the tool's supervision, the error just isn't observable anymore. And we also see such cases for must as well, where must just couldn't detect the error anymore because the execution basically was correct when you run the code under the tool's supervision. So one thing we do notice that, especially with those kind of transient error, the tools do struggle. An example would also be this error case here, where you have a broadcast of a floating point number and a broadcast of an integer, and these two broadcasts are logically concurrent, meaning there is no defined order between them. Obviously, this is an error, because if one rank executes the broadcast of the floating point number first and the other rank executes the broadcast of an integer number first, then those two broadcasts didn't match. And the bad thing here is that the correctness tools in this case only very rarely detects this as an error. I assume this is because the floating point number and the integer just has the same size. So it's really hard for the tools to detect that these two broadcasts aren't matching. On the good side, we do see that must is able to detect some of the data races, even if no buffer corruption is observed, because must has the integration of thread sanitizer and OpenMP correctness tools. And this way it was possible in some data race cases, not in all cases, to observe and warn there is a data race, although this time during this execution, we don't see any buffer corruption. But if you execute it 10 more times, you will likely see a buffer corruption due to a data race. And then the programmer could go ahead and employ proper synchronization in order to avoid that data race. We do see that the tools complement each other quite well. On the next slide, we will see that overall the tools do work adequately well given the complexity of the tasks. and the tools do complement each other. So there are some cases, for example, with collective operation that ITAC completely misses, but MUST can detect. And on the other hand, there are some other classes of errors, like with non-blocking operation that MUST completely misses, but ITAC can detect. So here we see, in general, the majority of cases can actually be detected by the tools. Yeah, not all cases can be detected, but we need to take into account that some of the cases, yeah, if you only detect the error in half of the executions, basically, yeah, then maybe, you can still improve the tool by getting the error more often. Of course, the discussion whether or not the error messages given are actually helpful is a subjective opinion-based one, so you may want to take this with a grain of salt here. In our opinion, we classified an error messages as helpful if it gives you more information than just a stack trace if the MPI implementation crashes. And this is the reason why in this view of classifying the error messages as helpful, ITAC is a bit less helpful than MUST, because in ITAC you sometimes just get the stack trace when your MPI implementation crashes. But of course, having these stack trace available may be valuable information as well. And we do see these kind of sending around uninitialized variable. You're using uninitialized private variables. Those kinds of errors are not detected by the tool, and as this is a quite common mistake in OpenMP, at least for beginners, to just forget about this. It may be a good idea if those kinds of errors are also included in the tools. On the positive side, when testing with correct cases, we don't see any false positive error reports. So if the tool reports that there is an error, there is probably an error. So in summary, we see that programming these kind of hybrid applications can become quite challenging. Yeah, the more and more threads, the more and more processes you have, the more and more challenging it gets, basically. And the tested tools do already have support for MPI plus OpenMP with MPI thread multiple threading level. They can detect a lot of errors, but there are still room for improvement. Some classes of errors, like sending around uninitialized memory, these are completely missed. And also where the tools can improve is these kind of transient error. Yeah, so the question you always have to ask if you have a hybrid application, and so is the ordering of execution correct just by chance or by proper means of synchronization? And this is a question that the tools currently cannot answer all the times. At least sometimes we see, for example, with the integration of thread sanitizer into MUST, that in general it is possible to answer such question. But the support for answering those kind of questions is currently limited in the tools. And also, if you execute the application, if you need to execute the application multiple times in order to observe the error, of course, it would be a good idea for the tools, even if the error was not present in this given instance of the execution, the tool still tells you about, okay, there is an error and you should probably look into it, so that also the tool is more user-friendly. And this is the main reason why we think that a pure MPI or a pure OpenMP correctness tool is not sufficient in these cases, because you really need to take into account both the semantics of the MPI call and the semantics of the OpenMP synchronizations in order to find out that question if the ordering of execution was correct by proper means of synchronization or just by chance. Yeah, so if you want to have a more detailed look, just drop by our GitHub. You will find all the test cases and then the explanation of those test cases there. So with this, let me thank you for your attention and hope for an interesting discussion.
Any questions for our speaker?
Thank you. What's the rate of false positives that you see in these tools?
There were no false positives.
No false. Okay. So, what's the balance between the number of bugs cases versus the number of cases that don't have a bug?
Yeah, we have like 50-50, roughly, not exactly 50-50, but roughly.
Oh, okay. All right.
Any other questions? I have one. Have you had any contact with the tool developers themselves to see any feedback that they have or response to these sorts of?
Yeah, our contact with the tool developers so far was basically limited to how we employ the tools properly, how to use them properly.
Gotcha. Yeah, it seems like it would be very useful for them to be able to incorporate this into their own development. Let's thank our speaker one more time. Thanks.